Hello everybody, this is Mr. Henson, and in this lecture we're going to talk about enzymes. We're also going to talk about this word here called metabolism. So what do we mean by this term metabolism? You've probably heard of the people having fast metabolisms, slow metabolisms, and you often kind of relate it to how skinny they are or how overweight they are. But actually really doesn't mean it has anything to do with that. The term metabolism simply means all the chemical reactions that are occurring in the cells of a living organism. Okay, so it's the sum of all the different chemical reactions that happen. The different types of reactions we have ones that we call anabolic reactions, which is where we're building up large molecules from smaller ones. And that usually requires a little bit of energy to be put in. So, for instance, the building up of amino acids into proteins would be an anabolic reaction. And we have catabolic reactions, which is where large molecules are broken down into smaller ones, which often releases energy. Now, the way those different reactions work is by using this idea of enzymes. You've probably seen enzymes in Key Stage 3, and you know that enzymes are examples of what we call a biological catalyst, which means they speed up chemical reactions, which is really, really useful to us. Now, if we didn't have enzymes involved in our chemical reactions, they would happen over 1 million times more slowly. So you can imagine if it took 1 million times longer to digest the food that you ate last night, you'd be digesting it for a very, very long time, which wouldn't be good at all. Okay, so let's have a look at enzymes and what they do and how they work. Okay, so as we mentioned before, enzymes are protein molecules, and so what they're made up of is amino acids. And each enzyme molecule usually consists of between 100 and 1,000 amino acids. They're joined together in a long chain, which is often folded to produce a unique 3D structure. So imagine this as being the unique 3D structure, and if we were to get a really big, strong microscope and look inside it, we'd see these amino acids joined together, forming this polypeptide chain or long chain of amino acids. Okay. Okay. So look at the structure of it. You can see it's got a very, very interesting structure. Kind of almost looks like a piece of a jigsaw puzzle, which has this area here that's been sort of cut out of it. Okay, and so we're going to come a bit closer to that now. So enzymes are very large, but only a small part of their structure is actively involved in doing its job. Okay, so in any enzyme, we've got an area of that enzyme we call the active site. Okay, now I'm going to run through this little animation, and I'll show you what happens. So the first stage is where all the enzymes have an active site, and molecules that do not fit the right shape are unable to find the active site. So you can see these different molecules coming into the enzyme and not actually attaching because they don't have the right fit. So that's the idea of that, is to show that the enzyme is specific. Okay, it will only attach to a certain type of molecule. All right, so when the correctly shaped reactant molecules have the ability to bind to the enzyme at the active site, and we can say that the reactant, which is this, fits into the lock, which is the enzyme's active site. So this would be the key, and this would be the lock. And we call this the lock and key hypothesis, or the lock and key model. The enzyme makes the reaction happen more easily, and the reactant breaks down into what we call two products, which are the things left over. The reactants leave the active site, and the enzyme is then free to accept another reactant molecule. Okay, so enzymes, as you can see, are very, very important molecules in all chemical reactions that happen in humans and in all animals, in fact, and all living organisms. They're not living organisms, they just help the reactions along, okay? But they can be affected. There are certain factors which can affect the activity of the enzymes, which is what we're going to talk about now. Now, if the temperature and pH changes sufficiently in an organism, either above or below the optimum, the shape of the enzyme can change. Okay, and we say it may become denatured. So here's a normal enzyme, and if it gets too hot, or the pH, if it's too acidic or too alkaline, you can see the active site shape change, and it wouldn't accept any more any substrate to break down, which is the things that get broken down. We call that the substrate. Okay, so let's have a look at a graph of that. Now, here's a typical graph of an enzyme, a rate of reaction here and the temperature along here. So you can see at low temperatures, okay, so between 0 and sort of 30 degrees, as the temperature increases, the rate of activity or the rate of reaction actually is increasing quite steadily. Okay, and it carries on increasing up until 37 degrees, which is what we call the optimum temperature. As the temperature continues increasing, the enzyme activity or the rate of reaction drops very quickly. Now you can see it's a much quicker drop there. This line is much more steep than this side, okay, indicating that it's rapidly falling. Okay, so at 60 degrees, we can say this enzyme has become completely denatured. So let's talk about that a second and why is that happening. So you can see between 0 and 37 degrees, as temperature increases, okay, that means there is much more kinetic energy being transferred to the enzymes and the substrate, which means they're going to move more quickly, and there's more chance of a successful collision occurring between the substrate and the enzyme. Okay, remember, a reaction will only occur if the substrate and the enzyme hit each other at the right angle. Now, if they're moving more quickly, there's more chance of those collisions happening, and more chance of the enzyme and the substrate finding each other and combining. Okay, so below 37 degrees, okay, it's not denaturing, it just hasn't got as much energy. Okay, so at 37 degrees, we've got the perfect balance. We've got the right temperature to give it the maximum amount of kinetic energy, okay, before the heat starts to damage the chemical properties of the enzyme itself and starts changing that active site. So you can see here after that, the enzyme becomes denatured. Okay, so the active site, the structure of the active site is changing dramatically, and it's not going to fit anymore. Okay, and that's the explanation for this very steep drop here. Okay, here's the graph we might get with pH. So you can see pH 6, 7, 8, 9, and 10 along the bottom. If you remember your pH charts, you'll remember that pH 7 is neutral, 8 is alkaline, okay, 9 is increasing alkalinity, and 10 is much higher alkalinity altogether. So you can see the optimum pH for this enzyme, where its enzyme activity is at a maximum, is at pH 8. Now you can see the graph on either side of this is almost identical. Okay, now what that means is that either side, there's a very, very narrow range of pHs that this enzyme really likes to work in. And you can see the sudden drop in enzyme activity with any big deviation from the optimum pH. And that's shown by this very steep drop either side. So any small deviation in pH means that it's going to denature. So if it's below pH 8, okay, it's denaturing. And if it's above pH 8, it's denaturing. Okay, remember that change is irreversible. Okay, and that's very important. Once the enzyme is denatured, it's not going to work again. Now we can get a slight denaturation. So at pH 9, for instance, the enzymes are slightly denatured, but not fully. So they're still working, but not at their maximum capacity. The same at pH 7. But you can see here at pH, well, just below pH 6 and just above pH 10, the enzyme is completely denatured. Okay. All right. Thank you very much for watching, everybody. And I look forward to doing some enzyme experiments with you in class.